I thought that let's just do one example of tensor calculus to help you guys in the practice sheet. So let us say we want to calculate gradient of the magnitude of the position vector. Okay, so R is basically the magnitude of this, let us say, vector. So it is essentially x1 square plus x2 square plus x3 square. So let us say we want to calculate the gradient of this R. Okay, so any ideas how will we proceed? How do we start this? How do we start attacking a problem like this? Yeah, but how do we start differentiating? So one is obviously a way which will probably not fetch you the full points in the exams, and that is okay, fine, I'll write this explicitly as a derivative with respect to x1, as a derivative with respect to x2, and derive the result. Okay, but if I'm specifying that you have to do this with index notation, because for more complicated problems doing that explicit differentiation will not really help you, but you can take help from the idea that you use for explicit differentiation, and that is that R is this. So basically R square is something that we can write in index notation like this. Okay, R square is xi. So when I take a gradient of this equation, what I get is 2R grad R equals xi grad xi plus grad xi times xi. Okay, now these are scalar times vector, so things can commute. So this is essentially 2 times xi grad of xi. Okay, and this is 2 times r of grad r. So from here you can say that grad r is going to be xi over r times grad of xi. Now what is this grad of xi going to be? What is grad of xi? So grad we defined as E hat I del by del xi. Can I apply this to grad of xi? Can I apply that to grad of xi? If I define my grad like this, then is this valid? We'll have to change the index in the definition, and that doesn't matter because it's anyways a dummy index. So instead of writing ei del by del xi, you have to write it like, let's say, ej del by del xj, and then grad of xi gives you e hat j del xi by del xj. Now xi's or xj's are components of the position vector. Naturally they're going to be independent. Okay, we are trying to differentiate this for an arbitrary point. We are not specifying that the point is on some curve or a surface where x1, x2, x3 might be constrained with one another through some equation. That doesn't exist. So xi's and xj's are independent. If xi's and xj's are independent, then what is del xi by del xj? What is that going to be? Delta ij. So this is going to be E hat j delta ij, which is simply E hat I, right? So grad of xi is simply E hat I. So grad of r is xi E hat I over r, which is what? Which is the unit vector in the direction of x, right? So this is your unit vector in the direction of x. This is simply x vector by r. Okay, which makes sense also. So this, if you read, what is it? This is the rate of change of the magnitude. Okay, we want to know the rate of change of magnitude when I change the vector. Okay, so the rate of change of magnitude when I am changing the vector. Okay, so the magnitude will be changing in the unit vector's direction only. Okay, so if you look at grad r, then this makes logical sense, and if you follow from here and explicitly calculate del by del x1 of this, del by del x2 of this, del by del x3 of this, get the same result. Okay, so notice the steps here. Okay, these steps are going to be important when you look at more complicated problems, for example those in your practice sheet. Okay, so please pay attention. Any questions in this? Excuse me, no, please, if you cannot write, then I don't know, I have already uploaded the notes, no, so what's the point? Any questions? All right, there are no questions. So if there are no questions, then we'll begin with continuum kinematics. So usually when we talk of fluid kinematics, probably in your APL 106, you were left with the discussion of streamlines, streak lines, path lines, and that's pretty much it when it comes to fluid kinematics. Okay, but of course those lines and discussion of those lines and curves is very important, but there is a whole lot more to continuum kinematics and fluid kinematics than meets the eye in those discussions. Okay, so today we'll try to relate everything from kinematics of continuous media. Okay, so this, if you really think about it, this is the true extension of whatever you covered in APL 100. Let us say the engineering mechanics course, that was all rigid body dynamics. The next step from rigid body dynamics is supposed to be deformable body dynamics, and there is no as such differentiation in deformable bodies of solids, fluids. That's just something that our department sort of reinforces. But you can have solid like characteristics in fluids, you can have fluid like characteristics in solids as well. Okay, it's just for for instructional purposes, it's easier to differentiate between the two and teach them separately. Okay, so continuum mechanics is the field uniting them, both solid mechanics and fluid mechanics. Okay, basically mechanics of deformable media. So whenever we talk of deformable media, it is very important to entertain the fact that when you start with some configuration, let us say this is called the reference configuration, you start with a reference configuration, you go to the deformed configuration. Okay, deformed configuration at some time t, and in the reference configuration, let us say you have a material particle, you have a material particle denoted by capital X. Okay, you track that material particle and you see what is the spatial location of that material particle at time t, and let us say that is small x. The mapping which maps this capital X to small x is, let us say, given by this p vector, which is called the deformation map. So the definition goes that this small x, the new spatial location of the material particle capital X, is given by p capital X. So I'll write capital X like this, t. Okay, and this is called the deformation map. Okay, this is called the deformation map or deformation function. Okay, for you guys, we don't need to make the differentiation that this is particularly a map, not a function. And you can think of it like a deformation function, and basically it is mapping the material particles in the reference configuration to a spatial location. Okay, at some time t. Now before we go ahead and do the algebra and calculus with this deformation map, it is important to think about what do you mean by a material particle. Do I mean a molecule? Do I mean a collection of molecules? If I mean a collection of molecules, how large is that collection of molecules? Okay, so whenever we discuss continuum mechanics, we disregard any atomistic structure of any material. Okay, we don't even consider that something could be made up of atoms. Okay, we say that at any spatial location, however fine you pinpoint the location, you're going to find a large number of particles, and the density is defined very robustly there. That is let us say I can, if I keep zooming in and I reach a space of volume delta V, and let us say you have n as the number of particles or number of atoms, molecules per unit volume, then we say no matter how small delta V is, n delta V is always very large. Okay, no matter how small this volume is, no matter how much you zoom in, which is of course not a good assumption when you consider this delta V to be orders of, let's say, angstroms or nanometers. Okay, and that is exactly where the laws of continuum mechanics start to break down. But we are not going to look at those microscopic and nano scales. We are going to look at what is known as a macroscopic scale. So we are going to look at fluid, let's say, in a room. We are going to look at fluid in a beaker. We're never going to look at fluid in a, let's say, nano channel or a micro channel. Okay, so continuum mechanics, this is the assumption you can think of for the continuum mechanics. In the notes that I upload, I give a statistical derivation of this, or statistical derivation of how this assumption helps you. Okay, you can think of placing different molecules in a bin of delta V. You can link that to Poisson process. You can apply the limit of n delta V much greater than 1, and then you can see what does this limit mathematically yield. Okay, but we are not going to look at that. That's some detail which you, if you are interested, you can look at. And the idea here is that if this assumption holds, then density of material is a continuous function of space. So the idea is that no matter how much we zoom in, as long as we are under the umbrella of continuum mechanics, no matter how much we zoom in, we are never going to encounter discrete particles. We are always going to encounter a huge collection of particles for which a density is well defined. Okay, a very mathematical analog of this is that how many integers are there? Let's say how many integers are there? What kind of, okay, how many real numbers are there? Is the number of both of them equal? One is uncountable infinity. So when we look at discrete nature of the material, we are saying that that there, if there is something like infinity, then it is made up of countably infinite particles. In continuum mechanics, we say that the material is made up of uncountably infinite particles. Okay, because we are not interested in, the spacing between the particles and things like that. Okay, so just like you have integers, you have infinity, you have an infinite number of infinities, and if you zoom out enough on the number line, you can, in an abstract world, you can say that, okay, I am going to say that the number of integers is also going to be uncountably infinite. Okay, so that is the idea of continuum approximation, that we are assuming that everything is made up of uncountably infinite atoms. So just like in real numbers, no matter where you point on the number line, you are going to land on a real number. So basically, no matter how pinpoint you something on the material, you are going to land on a large collection of molecules. So the density is well defined. Okay. Now having this discussion, it should reinforce in your head that this guy can never be a discontinuous function of capital X. Okay, we don't define anything that is discontinuous in continuum mechanics. We're not going to entertain in this course any discontinuities, actually neither in X or nor in time. Okay, we are not going to entertain that. Whenever I define a function, it is to be implied that these things are continuous and nice and all derivatives are defined. Okay. Now having done this, it is important to define what are known as Lagrangian and Eulerian description. So Lagrangian description and Eulerian description are two, let's say, two sides of the same coin. Okay, and what we say is, let us say there is a property, let's call it as temperature. Then temperature of a material particle at time t, we say I can define this as a field, temperature of all the particles which may be at x and time t. Okay, T is temperature, T could be any tensorial quantity as well. So the idea is that this is your Lagrangian or material field. This is your spatial field. Okay, the first one you can read it like temperature of the material particle that you have tagged while the body is moving, the temperature of that particular material particle which you have tagged and you are following it. Okay, the second one is, you know, the spatial location, you are looking at temperature of whatever particle comes at that spatial location at time t. Okay, so there is a change of reference in a way, that in the first one we are riding with the particle and we are seeing, okay, how does this particle, how does the temperature of this particle change and things like that. In the second one we are looking at a spatial location and we are saying, okay, well, how does the temperature change of particles that are passing through this spatial location. Okay, so when you have a Lagrangian field, so what is the deformation map? Is it a Lagrangian field or a spatial field? It's a Lagrangian field, right? So these two are equal. Okay, these two are equal when the capital X particle is at the spatial location x. So the way to write this is that T or capital T, whatever you want to call it, is equal to the spatial field. When you write this as okay, so this is how you relate the equality between the two. And again, the intuitive meaning of this is that the temperature, so here I am going to specify a material particle, you are going to convert that material particle's location to a new deformed location and tell me the temperature at some time, at that time whenever it is at that spatial location. Okay, so this is how you should read these two fields. Now tracking individual particles in fluid mechanics is very hard. Okay, in fluid mechanics tracking individual particles is very hard, although there are very nice Lagrangian theories in fluid mechanics, but we are not going to look at them. In fluid mechanics usually we look at spatial fields. Okay, we assume that the fluid is filling whatever volume or domain we are looking at, and we are going to look at the field inside that domain, how that changes in space and time. Tracking an individual particle is not our aim in fluid mechanics. Okay, and this could be any tensorial field. I just gave temperature as an example. This could be any tensorial field. Now what we can define using this deformation map is what is known as the deformation gradient. Okay, and this, before we define the deformation gradient, what I want you to entertain is that the basis vectors for which I use for capital X and small x could be different. Okay, here if you look at, I have not started small x and capital X from the same location. These are different locations. So the coordinate axis that I'm using for spatial location small x and the material location capital X could be different. So before we go ahead and define deformation gradient, I'm going to modify our nabla operator. So nabla I had defined like this. Here in continuum kinematics, our small x is the spatial location. So I'm going to define a nabla naught as something like this. So I'm going to denote everything that has to do with material coordinates with block letters. Okay, so the basis vector that I'm using to express my material vector is capital E hat. They may be same as small e hat. The only reason I'm writing them differently is to entertain the fact that they could be different. Okay. So capital E hat I del by del capital X of capital I. So the index is also capital, just to make that differentiation. So using this now, when I differentiate my deformation map, I get a second order tensor which is called the deformation gradient. And the definition is, as you might have predicted, it is going to be del phi I by del capital X j E j E hat I. Small or capital? Both are basis vectors. Okay, both are basis vectors. They could be same. I'm just writing them differently because they could be different also. There's no need for them to be same. Okay. Huh? So this is a vector. P, this map, this function is a vector valued function. So it is essentially phi I e hat I. Okay. That is where I get this guy. A more compact way of writing the deformation gradient is basically del x over del capital X. Okay. And a way to think about deformation gradient is that, let us say you have a line element dx in the reference configuration. How does this vector dx, how does this vector get mapped in the deformed configuration? And the answer is that, let's say this is your dx, then dx is basically f times d capital X. Okay. In the index notation, what I would say is dx I equals f I capital J d x j. What is an assumption? No, why? From this definition, this is what it follows. This is there's no assumption so far. Why do you think this is an assumption? So you can prove from here, what you can do is you can take a capital X1, you can take a capital X2, you can map them to a small x1, small x2, applies Taylor's expansion, and then you will get this result. Okay, by this definition. It's just a, yeah, it's a gradient of a vector field. No, let's go back to yesterday's class. Nabla is not a vector. We define nabla like this. Whenever we define gradient, so when we defined gradient of a scalar, what was the result? What was gradient of a scalar? A vector. So after that, I said that gradient raises the rank of the tensor. So if you're applying gradient on a vector, what are you going to get? A second order tensor, to be exact. A tensor, yeah, but a second order tensor. You can think of it like a vector, but it's not a vector because it does not transform like we have defined vectors to transform under coordinate transformations. In some textbooks, you may see this written as f dot with dx. Okay, and that is important because, so if you don't write a dot, then you are assuming it like a matrix column vector multiplication. Okay, a dot will specify that you write f, when I write, let's say, f dot dx vector, then I'm going to write it as del phi I over del capital X j E j E hat I dot with dx, let us say capital K capital E hat K. Okay, and only then I can say that E hat j and E hat k, since we are looking at Cartesian coordinates. So, this is going to give me delta capital J k, and then I can replace this k with j or this j with k. Okay. So, whenever we write this dot product, only then things will make sense if we are defining our tensors like this. Other way is to just think of it like matrix multiplication and immediately reach the conclusion in terms of index notation. I leave that choice up to you. You can either go this way and then writing this as, okay, you can either go this way, or you can not think about the dot and visualize everything as a matrix and a column vector product and just write it directly like this. Okay. So, once we have defined this deformation gradient, then an interesting quantity that we need to define is the determinant of the matrix defined by this deformation gradient. Okay. Things may seem very slow for now, but soon you will see everything falling in place when we use all of this to derive Reynolds transport theorem. Okay. The aim of all of this is going towards Reynolds transport theorem. Okay. So, things are interesting when we look at the determinant of this, of the matrix defined by this capital F. And before I do that, let's say, let us define dx, dy and dz. So, these are not x, y, z vectors, I am just labeling them with x, y, z. They need not be orthogonal. Okay, they need not be orthogonal. So, this is dx some vector, dy some vector in the reference configuration, and this goes to, let us say, a dx, dy and a dz. Okay. Under this deformation map, that set of vectors goes to this set of vectors. Now, there is a parallelepiped defined for both of these set of vectors, and what is the volume of that parallelepiped? How can we write the volume? If you know these vectors, what are the volumes going to be? What is, let us say, dv naught going to be? Huh? Scalar triple product, right? So, basically you will say that it is equal to dz dot dx cross dy, and let us put a mod just in case. That is what our volume is going to be. Okay. Similarly, the volume in that is going to be d small z dot dx cross dy, like this. Okay. Now, using this, using this transformation of a material vector under the deformation gradient or deformation map, to be exact, this transformation we can write that dv, so I want to write dv is going to be mod of, so we have dz dot dx cross dy. So, dz I can write like this. So, let us write everything in index notation. So, first when I write this in index notation, what do I get? Dz dot dx cross dy, what do I get in index notation? Can someone quickly do the algebra and tell me what is dz dot dx cross dy going to be in index notation? So, use your alternating tensor, the third order tensor that we defined yesterday. So, how do we write it in index notation? So, since I am uploading the notes, these are the chances that you should take to write things down from your hand, because if you are going to take the notes, I know you are going to open the notes one night before the exam, you are going to read through and hope that they help you in the exam. I'm again saying they will not. Okay. But this is a good chance to make things go through your muscle memory and understand and ask questions. So what is it going to be in index notation? How do I simplify this? Epsilon ijk, and then huh? Epsilon ijk y dxi. Huh? Yeah, so tell me all three indices. The way it's written, that would be the case, but we know that for a scalar triple product, I can rearrange things. Okay, and you may find that you can also define it with dxi dy dzk. That is all a matter of algebra, and you should be able to define, because I have anyways put a mod here, so I don't care if it becomes minus, something becomes minus, that should not be a problem. Okay, so anyways, so having written it like this, now let us use this here. So what am I going to get? Epsilon ijk. Now that dxj is going to give me what? Hmm? Dxj is going to give me what? So let's think of dzi first. So this is going to give me, let's say, f small I capital I dz capital I, and then f j capital J dx capital J, and then f k capital K dx capital K. Yeah, I told you, no. So this is going to be the same if you swap the indices according to the epsilon ijk rules, and even if you don't swap it according to the rules of epsilon ijk, when epsilon ijk is 1, doesn't matter if it becomes -1, because I put a mod there. The only reason I wanted you to write it like this is to think of, when I'm writing this kind of a expression, how are you going to convert it into index notation? You're right. No, so dx cross dy, when you break it into epsilon using index notation, it will be epsilon I j k dxj dyk e hat I. So dx cross dy, you can write it either as epsilon ijk, or let's say you write epsilon k ij dxi dyj e hat k. Okay, you can write it like this, or you can write it like epsilon I j k dxj dyk e hat I. It doesn't matter, please pay attention here. All of these are summed over. So I can replace I with j and j with I in all indices, in all expressions. Okay, so don't overthink this. You get this, and you can get all the permutations possible with replacing i's with j's, j's with k's, and so on. Okay. Yeah. So this can also be written as, so the only reason I've written it j here, so this could also be written as, so j is again a dummy index, no? So it could be this also. Again, capital I and small I are not the same. Capital J and small j are not the same. Capital K and small k are not the same. Okay. So this could also be written like this. Okay. I've written the like this here, if you look at it closely. So it is, you have to think a bit, but you don't have to overthink things. But even if you are overthinking, it's good if you ask questions. Okay. So this is the result that you get, and let's say we can write here that it is epsilon I j k f I capital I f j capital J f k capital K. and then I'm going to write it as dzi dxj dxk, and that is going to give me something very interesting. Yeah, thanks. This is d. Uh, so here I think I made a mistake. This should be dyk. This should be dxj dy. Thanks. Now, something that I'm going to ask you to confirm for me is, let us say I define a matrix like this. So this is, let us say, a matrix given to you. Okay. How do we write the determinant of this? How do we write the determinant of this? Huh? How do we write determinant of this? Diagonal product? What is diagonal product? What do you mean by that? So the determinant is something like this, right? And then expanding with this with a minus sign and then this. Okay. Now using index notation, you will discover using index notation, this can be written like epsilon I j k ai1 aj2 and ak3. Okay. You will discover that using epsilons, this is how you can write the determinant, and I invite you to open this up for all possibilities of ijk and confirm that this equals that determinant. Okay. There is no first principles derivation of this that at least I am aware of. To me, this is like, yeah, this is one expression, you try to write it using epsilons, and this is what you get. Okay. Now the idea here is that if you look at this expression, then this is very closely related to the determinant. How? The reason why this is closely related to determinant is, if I replace, so let us say I swap out, so let us say I write epsilon I j k f small I capital J f small j capital I f k capital K. So let us say I have swapped capital J and capital I. Okay, let us say I have swapped capital J and capital I. Now to keep an equality between the two, what I am going to write it as is epsilon. So I am going to swap small I and small j also. So this is going to be small j I k f I, or f rather f j capital J f I capital I f k capital K. So this swapping of indices is something that I can do because these are dummy indices. Now one thing that you should look at very carefully is that epsilon I j k is equal to minus of epsilon j I k. Okay. So what happened here is swapping the two indices, swapping the capital indices I and j. Once I swapped the capital indices I and j, I got a minus of the expression. So that means, that should give you a hint that this is antisymmetric in capital I, capital J and capital K as well. And as it turns out, it can be written as some constant times capital epsilon capital I j k. Okay. Whenever you are reading your notes, take a moment to convince yourself that this expression I can write as some constant times epsilon capital Ijk, because the swapping properties of this expression with respect to capital Ijk match the swapping properties of epsilon capital Ijk. Okay. So it's like if I tell you that there is a tensor, and if you swap the two, there's a second order tensor, you swap the two indices and the value doesn't change, then you are going to immediately write it as some constant times a symmetric matrix, right? So that is what I've done here. I understood that the swapping, after swapping, it behaves same as capital epsilon capital Ijk. So I've written it as some constant times epsilon capital Ijk. Now epsilon capital Ijk is 1 when I is 1, j is 2, k is 3. but when you put I is 1, J is 2, K is 3, you get this, okay, which means that this constant is actually determinant of F. So we haven't swapped small ij as in swapping, because ij were dummy indices, but capital I, capital J were not dummy indices. That is what you should, yeah, that is what you should take care of. I have not swapped small I and small j. Once I swap, I can swap small I and small j without changing the meaning of the expression. But as it turns out, I cannot swap capital I and capital J without changing the meaning of the expression, because capital I and capital J are not dummy indices, they are free indices. So be careful with that. Okay. So this swapping thing we are going to do a lot when we look at velocity gradient decomposition and things like that. This swapping is very useful in those cases. But the key thing here is that this expression I have written it as determinant of f times epsilon capital Ijk. And now we are in business, because I can write dv as mod of determinant of f times epsilon I jk times dzi dxj dyk. And that guy is basically determinant of f mod times dv naught, right, times dv naught. So what this tells you is that the determinant of this deformation matrix actually gives you the information how the volume is going to change when you go from reference configuration to a deformed configuration. Okay, and as some of you might have already predicted, that in fluid mechanics we are not related in the change in volume, we are rather interested in the rate of change in volume. So soon we are going to look at not the determinant of f, but the time rate of change of this determinant of f, and that is what helps us in deriving the Reynolds transport theorem. Yeah. Yeah. That is what I'm trying to say, that you cannot swap the free indices without changing the meaning of the expression, but you can swap the dummy indices without changing the meaning of the expression. That is the whole point. Yes, they are free indices. They are free indices. Capital I and capital J in this expression, forget about this for now. Capital I and capital J in this expression, they are dummy indices. Okay, this is like a third order tensor in capital I, capital J, capital K. That is the whole point. Okay. Okay, so this is detail. If some of you believe in, let's say, memorizing, then you can just say that, okay, I am going to just memorize this and screw all of this derivation, I don't care. Okay, that is also fine with me. Okay, but I just did this derivation so that you guys can at least start to see some coincidence between, all the solid mechanics courses, your fluid mechanics courses, and sometimes what people end up doing is thinking about them differently, but they're not different. So that's why I did this derivation, to assert that they come from the same discussion of continuum mechanics. But if you don't care, this is what we have, where this J is called the Jacobian and defined as the determinant of f. Now I have put a mod there. Okay, if there is no deformation, then what is J? 1. Okay, can J become 0? As far as we are looking at continuum mechanics, we do not allow J to be 0. If J is 0, that means f as a matrix is non-invertible, which means that for a spatial location I cannot find any material location. I cannot invert this map. We're not we're not interested in those kind of deformations. We're always, yeah. Yeah, because so this expression is not determinant of f. No, capital I, capital J, capital K are free indices. It's a third order tensor in capital I, capital J, capital K. Just that part is not determinant of f. When you have a specific combination of capital I, capital J, capital K, then it is determinant of f. That is my point. Okay. In other combinations also it could be either determinant of f or minus of determinant of f. Okay. And when either of I, J, J, K or I, K, if there is any two pairs that are equal, then you will see that this expression is actually 0. You confirm that using a 3 by 3 matrix, you will find that out. Okay. If either of these capital I, J, let us say capital I and capital J both are 1, you will discover that when you expand it in this way, it is 0. So the properties of this tensor alone, forget about this part, this tensor alone are similar to epsilon ijk, which is why I've written it as some constant times epsilon ijk. Okay. So this is an important expression for us. Okay. Now I'm going to write some more expressions which actually you can derive. So I have written here that epsilon small ijk f I j f f I capital I, f j capital J, f k capital K is actually this determinant j times epsilon capital I j k. Okay. Now there is another way in which I can write this j as, and that is j is going to be 1 by 6 of epsilon I j k small I j k f I. Okay. I'm not going to derive this or prove this. If you guys want, you can do it by multiplying on both sides by epsilon capital I j k. And then yesterday we saw what is epsilon I j k times epsilon I j k. Yeah, from epsilon delta identity we derived the value is 6. So that's where this 1 by 6 comes from. So it's very straightforward. Okay. And there is another interesting property which again I am not going to prove for you. So that is f inverse, the matrix that is represented by f inverse. Okay. And the ji component of that is actually equal to 1 by 2 j, this j is Jacobian, epsilon I p q epsilon j k l f small p k f q l. Okay. There is no need to prove this. If you want to memorize it, it's fine. If you don't want to memorize it, that is also fine. We are just going to use this once in our derivation. Actually, let me not use it in any derivation. Let me just give you the result that I am going after, and the result is what is del j by del f I j. Okay. Just like I started this class by differentiating the magnitude of a vector with respect to that vector. Okay. So in a very similar analogous sense, what I am doing here is I am differentiating the magnitude of a second order tensor with respect to the components of that tensor. Okay. In some way, this is like a higher order version of grad of r that we just discussed. Okay. This is this is not gradient in any form. It's just looking at how does the magnitude change per unit change in any of the components. That is what we are looking at. Okay. And this actually comes out to be j times f inverse ji. Okay. Which you can write in the direct notation as this is going to be j times f inverse transpose. Okay. No need to memorize them. We are just going to use these is just going to use this in a bit. And actually you could differentiate this part, you could differentiate this expression, use this to prove this. Okay, you can differentiate this and use this to prove this expression. Maybe that will be your quiz question. It's all just index notation. There's nothing matrix intensive that is going on here. It's all just index notation eventually. Now we keep this here. We are going to come back and use this result soon. Before we get to that, as I said, in fluid mechanics, we are not interested in the deformation per se, we are interested in the rate of deformation. Okay. So to get to that, we have to first define what I mean by rate, or rather rate of change. Okay. So rate of change basically implies rate of change of any quantity. Now when I say rate of change of any quantity, do I mean a Lagrangian quantity or a spatial quantity? So if I'm defining, let us say, rate of change of temperature, if I'm defining rate of change of temperature, then that is basically del, if you recall the definition, it is this guy, keeping this constant, keeping the material particle constant, I am looking at the rate of change of temperature. Is she okay? Hi, are you okay? I hope you're fine. If you're not fine, it's okay to leave, I think. So T dot, I'm going to define, which is the rate of change for a specific material particle. Okay, we are looking at it for a specific material particle, and this is exactly what is written as dt by dt, which you guys probably call as the material derivative. Okay, we define the derivative for material coordinates. We give a new notation when we are writing that derivative for spatial analog of that property. Okay, so this capital D by capital dt just means that, okay, in terms of spatial field, what kind of derivative we are looking at. I have still not defined what is this capital D by capital dt is. I'm just giving it a name, I'm just giving it a symbol or a notation. Okay, just think of it like that. There's no derivation that has happened yet. So in this regard, we define the, let's say, material velocity as, so we'll define the material velocity as, so what is the corresponding position vector, that is basically defined by, this is how I'm going to define the material velocity, or you can think of it like x dot, or you can also write it like phi dot, where phi is your deformation map. The corresponding spatial field I am going to denote with a u, which is what we are going to continue throughout the course, and that is basically u of x comma t is equal to capital V of capital X comma t. So the way to read it is the velocity of the fluid particle tagged with capital X when it is at spatial location small x, at that time it is equal to u. Okay. So it is always, whenever we are discussing spatial fields, we are always relating it to the Lagrangian field somehow, because if you think about it, all of the laws of physics, when you say, okay, mass of this particle is not going to change, momentum of this particle, rate of change of that momentum is equal to force, all of these laws of physics were defined for particles. They were not defined for random spatial points through which particles may be passing, may not be passing. So to get to the governing equation of fluid mechanics, whenever if we have decided that okay, I'm not going to look at Lagrangian fields, I'm going to look at spatial fields, I need this relation every time, because I'm going to use the laws of physics to derive the governing equations of the spatial fields, but laws of physics don't exist for spatial fields. They exist for Lagrangian fields. They exist for a point or a collection of points, rigid bodies, deformable bodies, whatever. Okay. So this is why this equivalence, always making this equivalence, is important. Okay. And the way we define this material derivative, let us say, is we are saying that it is equal to d of t when it is a function of x comma t dt. Now notice that this x itself is a function of capital X comma t, and the whole idea of this partial differentiation was we have to keep the capital X constant. We don't need to keep small x constant. We need to keep capital X constant. So this capital small x is defined as so this is what we have to do. You have to keep the capital X constant. We are looking at rate of change of temperature of a particular particle. You have to keep capital X constant, and now you know that this small x could change with time. I'm looking at the rate of change, so you have to apply the chain rule here. Basically, you have to differentiate this in time. Okay, so this is going to be simply del T over del T, basically differentiation of temperature with respect to the second argument, keeping the first one constant, and then differentiation of temperature with respect to the first argument, keeping the second one constant. So okay, so not second one constant, by the way, we are not keeping this t constant, we are keeping capital X constant. Okay, we have to be very careful with that. We are keeping the capital X constant. So this is what your material derivative comes out to be, and this del x by del t is simply your velocity. Okay, so the definition of this is that this d by dt of t, capital D by dt of t, is simply, so again this is del x by del t, which is going to be your spatial field. So u dot, this guy is nothing but your gradient of t, which is what we looked at in our first lecture. Okay, and here this u dot gradient is basically the velocity magnitude times the directional derivative of this temperature. Directional derivative in which direction? In the direction of velocity. From your APL 106, what are those lines which are always parallel to velocity? What are those lines? Streamlines. Streamlines, the tangents to streamlines are always pointing towards velocity. So this is basically telling you what is the change in temperature as you move from one point to another in a streamline. So the rate of change of, let's say, temperature or any tensorial quantity, it's equal to whatever it changed at a given location. Again, look at it, it's a rate of change of temperature or any tensorial quantity of a particle, whatever it changed at a given location, plus whatever particle traversed in a non-uniform field. An example of this is, let us say the temperature of this room is constant in time, but it is not uniform in space. Let us say that corner is hot, that corner is cold. A particle travels from cold to hot corner, the particle of temperature changes, right? That is what this u dot grad t is. And this del t by del t is how the temperature field changes in time at any spatial location, irrespective of spatial location. How is this evolving in time? Let's say the room is heating up, cooling down, so the particle will experience the change. Okay, so think about this material derivative closely. We'll resume from here in the next lecture.